Hello everyone, welcome to lecture 27 part B of this online course on modern display technologies, flat panel display. We'll continue our discussion on the classification of the transreflective LCDs here. So in this video we'll basically cover those portions which were not covered in the previous one. So we'll be talking about the scattering plus absorption transreflective displays, the LC gel design, and then we'll talk about the reflection type, okay, the cholesteric with image enhanced reflectors, IERs, and then finally we'll have this comparison of absorption, scattering and reflection type of displays, leaving the phase retardation type design for the next lecture. Okay, so here is picture that shows the operating principle of the dye doped negative liquid crystal gel. Okay, so what is the design philosophy here? As you can see that there were, in the previous lecture we have seen the drawbacks of the scattering type liquid crystal gels drawbacks. There are mainly three drawbacks. So we plan to bring the scattering and the absorption features together and come up with a better solution. So let us think about the design philosophy here. A blank sheet of white paper scatters and diffuses ambient light in every direction, giving a bright wide viewing angle appearance with no glare. And where it is printed with ink, you will see that the ink basically absorbs light and that area looks dark. So the designers deliberately engineer an liquid crystal gel system that basically can reproduce both of these effects simultaneously, where they are scattering like a paper-like diffuse bright state, whereas the absorption via the dye is able to give you a genuinely dark printed looking dark state. Okay, so this is the design philosophy. So now let us look into the material system. So as I mentioned, this is the dye doped negative liquid crystal gel. So what is the genesis of this idea? The design basically uses a negative dielectric anisotropy liquid crystal, for example Mark ZLI 4788 with delta epsilon of -5.7, rather than a positive anisotropy nematic which is typically used in the earlier designs. Now these are mixed with a small amount of diacrylate monomer and dichroic dye, okay, S428 in the weight ratio of 90:5:5, and then a UV curing at a controlled low temperature of 13 degrees centigrade was done for 2 hours. That basically polymerizes the monomer into the polymer chains that grow specifically along the cell gap that is in the Z direction. Okay, and because the negative anisotropy liquid crystal molecules are aligned perpendicular to the glass, okay, so those are like homeotropic, and that is how during the curing process they basically grow along the cell gap. Okay, now a key manufacturing simplification here is that the polyimide alignment layers are deliberately left unwrapped, okay, because there is no preferred in plane direction. The dye absorption in the activated state has no preferred polarization axis either, making the whole device insensitive to the incoming light's polarization state, which means no polarizer is needed anywhere in the stack. That is going to maximize your brightness. Now let us see how the bright and the dark state works. So first focus on when voltage is not there, so there is the voltage off condition. So here what is happening, the liquid crystal and the dye they stay perpendicular to the substrate, okay. So very little scattering as well as weak absorption. So what you get is highest reflectance, okay. So you can clearly see the black ones are the dyes, the white ones are the liquid crystals, and these are the polymer network that you are seeing, and these are basically the ITO electrodes through which the voltage is basically applied, okay. Now you see in the application of high voltage, that is where you get the dark state. So you can consider the voltage to be driven at 1 kilohertz AC, that is done to avoid ionic effects in the liquid crystal, because the liquid crystal has negative dielectric anisotropy, and the applied field reorients the director away from the field direction into the XY plane, okay. So it can basically drag the molecule along with it. So what happens, this basically increases the scattering from the polymer network, and also it activates the absorption from the dyes, okay, and the combination can give much substantially darker state, okay. So you basically get more paper like dark state than either of this mechanism working alone, okay. So here this figure shows the voltage dependence reflectance of a dye doped negative liquid crystal gel, which is driven at 1 kilohertz frequency, okay, and the cell gap is considered to be 5 micron. Lambda is of the green diode laser, that is 532 nanometer, which is being used, and you see the curve is independent of the laser polarization. So what do you make out of this? So you are basically using a green diode laser at 532 nanometer, that is used here instead of a broadband white light source, okay. That is done because the gas torch system looks dark red rather than black, okay, and a dielectric mirror basically gives a double pulse, and a detector is sitting roughly 25 centimeter behind the sample, okay. That is typically the mobile viewing distance. Now let us explain this reflectance curve. So you can see at V equals 0, the liquid crystal is homeotropic, giving the highest measured reflectance, about 52%. As you can see, the voltage is increasing past a threshold, the reflectance basically drops off gradually after this point, and you can actually see that the curve is same for any input polarization of the laser, okay, and the experimental results also show that it is basically polarization insensitive. So that is an important achievement, that you are getting polarization insensitive behavior. Next, if you see the threshold voltage, okay, so it is basically raised to around 7.5 VRMS, okay, by the polymer network constraint, okay. So if you compare this with the unconstrained liquid crystals in the previous slides or previous lectures, you will see that those are only few volts, okay. So what you achieve from this is that at 20 volt VRMS, you see the measured contrast ratio exceeds 200:1. So if you compare this explicitly against the roughly 5:1 contrast ratio that we were getting earlier from the typical pure guest host kind of display, this is roughly 40 times more than the previous ones that we have got by adding this scattering on top of the absorption. Another important factor is that response time. The response time Here you'll see the response time. The rise time is typically 1 millisecond, and you have 4.5 millisecond decay. Okay, so the switching is taking place, say, from 0 volt to 20 volt, and this is what is the rise time and decay time. Okay, so this is also typically way faster than the typical guest host, where response time is typically 50 millisecond. So what you can understand that the polymer network basically accelerates the relaxation, okay, by providing the elastic restoring force. So here this slide particularly reconnects the reflection type transreflective LCD category to the cholesteric Bragg reflection physics already introduced in the lecture 26, where we have talked about one of the orthogonal polarization transreflector design. Okay, and we can identify here the core problem that must be solved before a plain cholesteric liquid crystal layer can be used as a working transreflective LCD pixel. So if you have a quick recap on this, the two governing relations from the previous lecture, you will see that the Bragg center wavelength, that is the lambda naught, is equal to the average refractive index times the helical pitch, that is P0, and the reflection bandwidth, that is delta lambda naught, is equal to the delta n, which is the liquid crystal birefringence, times the P naught, which is again the helical pitch. Okay. Now for full visible spectrum coverage with a single pitch, you have a requirement of delta n to be greater than 0.6, right? Now what is the problem for a normal display? The reflected and the transmitted circular polarizations are typically orthogonal to each other. So a plain cholesteric liquid crystal layer alone will give you a reversed contrast image. So these are basically unusable without using extra optical components. So what is the solution used here? You can basically add an image enhanced reflector IER on top of the top substrate, plus a patterned ITO and patterned absorption layer on the bottom substrate. So let us see this in the next slide here. Okay, so here you can see this schematic configuration of reflection types transreflective cholesteric LCD and the operating principle at the voltage off state. Okay, how it works. So here you can see the exact structure of the reflection type transreflective cholesteric LCD, okay, and how it works on the voltage of bright state, okay, in both modes, reflective mode and transmission mode, showing precisely how the added IR, that is the image enhanced reflector, okay, this one, and the patterned bilayers, okay, they are basically helping you solve the problem of the reversed contrast that you have discussed just now. So you see the structure once. So the image enhanced reflector or IR combined with a color filter basically sits on the top, okay. So this is the viewer side, okay. So it is basically sitting on the top substrate, right. On the bottom substrate there is another patterned ITO layer with deliberate openings that you see. These are the deliberate openings, okay, and a patterned absorption layer whose here also you can see the dark one will be absorbing, the bright one will allow. These are the openings, okay. So you also see there is a patterned absorption layer which are aligned directly beneath this IER, okay. Now because the ITO is absent right where the absorption layer is placed, okay, the electric field never reaches the CLC directly. Okay, so this is where the ITO is and this is where the absorptions are. So absorption layer is, so the ITO is basically present right where the absorption layer is placed. So that way the electric field, because here the electric field will be like this, but the absorber is slightly away, so the electric field never reaches the CLC directly below the IR. So that what happens, the specific region of that CLC directly below the IR, what happens, the specific region of CLC always stays in its natural undriven planar helical texture regardless of the applied voltage which is appearing elsewhere in the pixel. So it's slightly complicated, but you can see the structure carefully. So here you have the right-handed cholesteric liquid crystal layer. So this is the top substrate. Okay, there here you have the image enhanced reflector plus the color filter. Here you have the ITO which is fully patterned. Here you have patterned and some gaps or openings. Here you have the patterned absorption layer, and then here you finally have the substrate, right? So now let us see the voltage of bright step. Okay, so that is basically the voltage of, you are getting the bright state in the R mode. So let us see how it works. So in the reflection mode, you have the unpolarized ambient light that is hitting the CLC layer, okay, which are basically right-handed planar helix. Okay, so the right-handed circular component basically reflects straight back to the viewer. Okay, so you get a bright contribution. On the other hand, you can say the left-handed components which this CLC cannot reflect basically passes through, and it gets absorbed by this absorption layer which is placed on the bottom substrate, and this light is simply getting disregarded, okay, or you can say discarded, and it's not causing any reversed contrast problem because this portion of the light can never reach the viewer at all. Okay, in the transmission mode, what happens? In the transmission mode, you have light at the back, so your light is entering, the source is the backlight, so light is entering from the behind, or you can say right-handed circular component is basically reflected back by the CLC, which is either getting absorbed by this patterned absorption layer or it is recycled back into the backlight unit. Again, it is simply getting discarded. So what is happening? Only the left-handed components of the incoming light can basically pass through this this CLC layer, and it can strike the IR layer, that is the image enhanced reflector layer on the top substrate. Now reflection at this IR layer will introduce a pi phase shift, so that basically converts this light back into right-handed circular polarization, and this newly made right-handed light can now travel down backside, and critically is now the correct handedness to be reflected by the CLC layer, so it is getting reflected for the second time. Okay, and that it comes out for the viewers. So what you are getting is finally a bright transmission mode image with the same non-reversed sense of brightness as the R mode image. Okay, so once again, if it is complex, I can repeat it. So for the right-handed backlight, it is basically reflected or recycled by the CLC, okay, or it is getting absorbed by them, and the left-handed backlight basically passes through the CLC, but it gets reflected off this IR layer with a pi phase flip, so they now become right hand circular polarization, which is essentially reflected by the CLC layer towards the viewer. Okay, so that is there in the off state. Now in the on state, we will see what we get from this reflection type cholesteric LCDs. So in the on state, we are getting the dark modes or the dark states in the voltage on condition. Okay, and we will see what happens in the both R mode and the T modes. Okay, so here in this slide only we can complete the discussion of this reflection type transreflective cholesteric LCDs by covering its voltage on dark state, and then we can deliver a balanced assessment of the strength and weakness of this one to close out this particular category. So let us see how it works. So here is the explanation of the voltage on dark state. Now away from the protected region beneath the IER, okay, when you are applying the voltage, that basically switches the CLC's planar helical textures, okay, into a focal conic texture. Okay, so what you see is a disordered polydomain structure like this. Now in this case, if the domain size is well controlled and it is comparable to the light wavelength, that will scatter the incoming light forward rather than simply transmitting or Bragg reflecting it cleanly. So in the reflection mode, ambient light is forward scattered, okay, by this focal conic structure, and then they are basically absorbed by the patterned absorption layer, and that gives you dark pixel, right? Now in the transmission mode, what is happening, the backlight still first encounters this still planar kind of CLCs which is placed beneath this IER. Okay, so these are the IER regions, this one and this one, okay, particularly. So here, but what happens, light would otherwise exit towards the viewer is instead forward scattered by this kind of focal conic CLCs on its way out, and they are also basically getting absorbed by these layers. So in both cases you are basically getting this scattered light which is getting absorbed. Now what is the advantage here? Because this design uses zero polarizers, essentially none of the light budget is lost due to the polarizer absorption, which is normally a significant source of light loss in all other transreflective designs. Okay, now you consider the manufacturing cost. So it is challenging to produce these IER patterns precisely and aligning it pixel by pixel with the patterned absorption layer on the other substrate. Okay, you need to make it like that. Okay, so that basically makes the photolithography and the cell assembly much harder than simply having a uniform layer. So because here any kind of misalignment will directly cause light leakage, which will essentially degrade the contrast. So this kind of forward scattering focal conic dark state is never perfectly forward only in practice, okay, because some fraction of the incident light is inevitably back scattered as well. So that basically produces a translucent rather than a deep dark or deep black dark state. So this is conceptually in the same category of the problem that we have seen that limited the pure scattering type liquid crystal gel designed, which we discussed earlier, right? So now let us have a comparative summary of this absorption, scattering and the reflection kind of model. So the absorption type, we understood these are the simplest concept. You can use 1 or 0 polarizers, but the contrast is basically kept to near 5:1 only by the dyes dichroic ratio, and that is why a very small niche of the handheld market is scattered by absorption type of LCDs. The other one is the scattering plus absorption type. So this is the strongest performer of the three, and we have seen that you can go up to a contrast ratio of 200:1, and you can have sub 5 millisecond response time. However, they require larger drive voltage around 20 volt, and which is beyond the capability of the standard thin film transistors which are required to drive these LCD modules. The third one we have seen here is the reflection type, which is cholesteric plus use of this IER. So here no polarizers are required, so inherently you do not lose any light because of the polarizers, so you get high light efficiency, okay. But the alignment of the IERs step, okay, that basically adds real manufacturing cost and technical difficulty. And we have also seen that the dark state that you get from here is not completely black. So what is common across all these schemes is that each of this category chases high brightness by minimizing the polarizer count. So the polarizer is not going to help you. You get rid of the polarizer, you can get better brightness, and each pays basically for this brightness with a different practical cost. Either your contrast is getting limited, or you require a high drive voltage, or you add up more manufacturing complexity and cost. So you can understand that because of all these problems, none of these three has become commercially dominant. So that basically sets up for the motivation for the next lecture, where we will be discussing the phase retardation category, which basically accepts the two polarizer brightness penalty in exchange for the best all-round contrast, voltage and manufacturability. So it is a perfect trade-off that you can get in this phase retardation category. So here is a quick summary of this particular two lectures, 27 and part B, that we have recorded today. So the absorption type is dye based guest host kind of a system. You can have it in pneumatic or cholesteric liquid crystal. In both cases, the contrast ratio is typically 5:1, so it's only used for niche application. You can go for simple scattering or scattering plus absorption type with liquid crystal gel devices, where you can go up to 200:1 contrast ratio and achieve sub 5 millisecond response time, but the requirement of the driving voltage is high, around over 20 volts. And the reflection type allows you cholesteric layer plus image enhanced reflector, IER, okay. So here you get no penalty because of no polarizers being present, so they give you high brightness, but the manufacturing complexity is high, and also you are not getting a perfectly black pixel, okay. So each of these design that we discussed in this lecture and the previous, their concept was to minimize the polarizer count for brightness, but paying for that in terms of other practical cost every time, right? So as I mentioned, in the next lecture we'll discuss about the phase retardation time, which becomes the commercially most dominant category by extending the twisted pneumatic or mixed mode twisted pneumatic with two polarizers, and then by doing some cell gap engineering to come up with the best overall display performance. So with that we conclude this lecture 27 part B, and 27 was done earlier. So this basically ends here, and we'll start the discussion of the phase retardation liquid crystal design in the next lecture. If you have any doubt regarding this particular lecture, you can drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.